So good day to everyone. So in this video, we will start to analyze the Otto cycle. So in the previous video, we've discussed Carnot cycle. So now, let's try to analyze first the Otto cycle. So basically, Otto cycle follows the 4-stroke and 5-event cycle, wherein you have, so in the 4-stroke 5 events, you have, so first one is intake, then you have compression, then you have ignition, power, and exhaust stroke. Okay? So as you can see here, later on, once we analyze this one, we can determine what type of process does it undergo. Okay? So the first thing that you need to do when you are dealing with gas cycles is, I suggest, you always draw your PV and your TS curve. Okay? So what will be the use of PV and TS curves? So these curves will allow you to check your answers later on. So once we've answered questions pertaining to Otto cycle, they can verify if your values are correct or not. So an example of that is from point 1 to 2. So when you solve P sub 2, you are expecting, so based on the PV diagram, P sub 2 must be greater than P sub 1. Okay? So the first thing that we need to do is for us to analyze first what is the process. Okay? So we will start from point 1. Okay? So point 1 to point 2. So the first thing that you need to locate when you are dealing with gas cycles is to look for straight lines. It can either be vertical lines, straight vertical, or straight horizontal, both on PV and TS diagram. Okay? So let's assess first point 1 to 2 in PV diagram. Okay? As you can see, it is not a straight line in the PV diagram. So therefore, once it is not a straight line in the PV diagram, you look at your TS diagram, or temperature entropy diagram. As you can see, it is represented by a straight vertical line. So therefore, this straight vertical line corresponds to a constant entropy. Okay, so this one is, since the entropy is constant, so we can write it here. So at point 1 to 2, entropy is constant. So therefore, that is an isentropic process. Okay, point 1 to point 2. Next, what about point 2 to point 3? As you can see in the PV diagram, it is represented by a straight vertical line, which represent a constant volume process, which is an isochoric process or an isometric process. So we can write this down as V is equal to C. Take note that point 1 to point 2, point 1 is your initial position wherein your piston is at your bottom dead center. And then at point 2, once it goes up, so what will happen? It will compress the fuel and air mixture inside your cylinder. So once you've compressed it, what will happen? The pressure will eventually increase. Okay? Next, at point 3, so 2 to 3 is a constant volume process. Then 3 to 4, so once it is already compressed, so 2 to 3, once it is already compressed, you will apply your heat. That is your ignition event. Okay? So intake goes from 0 to 1, then compression from 1 to 2, then 2 to 3, that is your ignition, power, that is 3 to 4, then exhaust, that is 4 to 1, wherein heat rejection takes place. Okay? So as you can see, from 3 to 4, let's locate for another straight line. So 3 to 4 is represented by a straight vertical line in your TS curve. So therefore, 3 to 4, that is isentropic. And then 4 to 1 represented by a straight vertical line as well in your PV diagram, that is constant volume. Okay? So upon doing this, we can derive certain equations from this principle. So let's start first with efficiency. Okay? So let's erase this one. So in efficiency for all gas cycles, So it follows the general equation for efficiency, which is the efficiency is equal to the work net over QA. Okay? And work net, we know, is work net is equal to heat added minus the absolute value of your heat rejected. Okay? Because heat rejected, the magnitude of heat rejected should always be negative. Okay? Because it is rejected by your system. Next. So, let's analyze QA. Okay? So, it is said that it occurs in a constant volume process. So, if you recall, what is the equation of heat? So, the equation of heat, that is QA is equal to MC delta T. Okay? Or the changes in temperature. As you can see, or as we've mentioned in the previous video, so C, or your specific heat, is always dependent when you are talking about heat. So, C is always dependent on the process. So, this one is a constant volume process. Therefore, this should be CV. Okay? And then the changes in temperature corresponds to the limits. So, the limits here is T3 and T2. So, we can conclude that QA is equal to MCV T3 minus T2. Okay? So, next, what about heat rejected? So, for heat rejected, same goes with QA. Okay? So, that is M. So, what is the process from 4 to 1? This one is heat rejection. Okay? From points 4 to 1. Okay? So, therefore, that is M. So, since constant volume process, it should be CV. And then your limits, your final point, is T1 minus your initial, that is T4. Okay? So, lagi, final point minus initial point. Okay? However, this one seems improper. Why did I say that this is improper? Because 4 is an upper limit and 1 should be the lower limit. So, I can interchange these two. Okay? So, if I interchange those two, I will have MCV T4 minus T1. However, if I interchange this one, in order for the equation to be balanced, my multiplier here should be on an opposite magnitude. Okay? So, let's say that is positive, then it will become negative. Okay? So, let's mark this equation. Next. So, now we have QA. So, we can substitute everything in your efficiency equation. We will have efficiency is equal to work net, that is QA, minus the absolute value of QR, which is QA is MCV T3 minus T2 minus QR. So, we get the absolute value of this one. We will have MCV T4 minus T1. So, why is it still negative? Because we just get the absolute value of this one. We neglect the negative sign. Okay? So, over QA. So, QA, which is heat added, which is MCV T3 minus T2. Okay? As you can observe in the numerator, we have a common factor of MCV. So, we can factor that out. We have E is equal to MCV. So, this one is T3 minus T2 minus T4 minus T1 over MCV T3 minus T2. So, as you can see, I just factor out MCV. So, once I distribute this one in each term, we will return from our original equation. Okay? So, as you can see, MCV here will cancel out, leaving us with E is equal to T3 minus T2 minus T4 T1 over T3 minus T2. Okay? So, since they are sharing the same denominator, we can separate the two of them. So, you will have the efficiency is equal to T3 over T2 over T3 over T2 minus T4 minus T1 over T3 minus T2. So, as you can see here in this part, we can equate that to 1. So, because they have the same ratio. So, leaving us with the efficiency is equal to 1 minus T4 minus T1 over T3 minus T2. So, let's write this down as equation number 1. Okay? So, next. So, after equation number 1, let's try to analyze naman how are we going to solve for T sub 2. Okay? So, of course, you will start first at point number 1. Okay? You need to solve for P1, V1, and T1 as well. Okay? After that, you need to solve for P2, T2, and V2. So, how am I going to solve for this one? So, I can solve for T sub 2. So, we know that from point 2 and point 1, we have an isentropic relation or an isentropic process. So, therefore, I can use isentropic relation. So, T2 over T1 is equal to, so since I am using volume here, V1 over V2 raised to K minus 1. So, here in Otto cycle, I would like to introduce you as well to compression ratio. So, compression ratio is basically the ratio of your bottom dead center, that is V1, relative to top dead center, which is V sub 2. Okay? And compression ratio can also be resolved by using your clearance ratio or your clearance percentage, that is 1 plus C over C. Take note that the clearance should be in terms of decimal, not in percentage form. Okay? So, as you can see here, the compression ratio is V1 over V2. So, therefore, this entire term, V1 over V2, we can rewrite it as T2 over T1 is equal to RK raised to K minus 1. So, by solving T sub 2 on the left side, so cross multiply T sub 1, we will have T sub 2 is equal to T sub 1 quantity RK raised to K minus 1. So, this is equation number 2. Okay? So, what about solving for pressure? So, since it is a isentropic relation, therefore, we can use isentropic relation for pressure and volume. Right? So, here, I can solve for P2 by cross-multiplying P1. Therefore, I have P2 is equal to P1 is equal to quantity. This should be quantity. So, V1 over V2 here, this is your compression ratio raised to K. Okay? This is equation number 3. Next. How can I solve now for V sub 2? Okay? So, I can solve for V sub 2. So, since I am given, let's say I am given a compression ratio is V1 over V2, then I can solve for V2 by dividing V sub 1 over RK. Okay, or your compression ratio. So, you can solve T2, P2, and V sub 2. So, now you can immediately proceed with point 3 or point 2 to 3. So, this side is equal to C. We're done on that already. So, let's proceed with 2 to 3. Okay? So, how am I going to solve for volume 3? So upon observation on your PV diagram, so V sub 3, we've said that it is a constant volume process. So therefore, we can conclude that V3 is equal or same with V sub 2. So let's write that down. So V3 is equal to V sub 2. So same goes with V sub 1 and V sub 4. So you can see here, they are also isometric process or isochoric process. Therefore, V1 is equal to V4. Okay? Next, how am I going to solve for T sub 3? So I can solve that using equation of combined gas law. Okay? So in combined gas law, that is P3 V3 is equal to so let's use P sub 2 first. Okay? So we can use P2 V2, then P3 V3 over T2 and T3. So since this one is an isochoric process, so therefore volume will eventually cancels out, leaving us with if I perform separation of variables, I will have T3 over T2 is equal to P3 over P2. So this one is equation number 5. Okay, so I can immediately solve for volume, temperature, and pressure at point number 3. Okay, so what about point number 4? This one, 3 to 4. So I need to relate points 3 to point 4. So since it is an isentropic process, so we will use isentropic relation. So we will have T4 over T3 is equal to V3 over V4 raised to K minus 1. Okay? So if I want to solve for T sub 3 here, so what can I do is I can reciprocate the base of the left side. So I can rewrite this as T3 over T4. However, once I reciprocate the term on the left side, I must also reciprocate the base of the right side, which will lead me to V4 over V3 raised to K minus 1. Okay? But we've said V4 is equal to V sub 1. So I can rewrite this one as V sub 1 over V sub 3 is equal to V sub 2 raised to K minus 1, leaving us with T sub 3 is equal to, or T3 over T4 is equal to, so V1 over V2, that is your RK, raised to K minus 1. So solving for T sub 3, so I can cross multiply this at the right side. I will have T3 is equal to T4 RK raised to K minus 1. So this is your equation number 6. Okay? So what about the pressure? So pressure, so that is P4 over P3 is equal to this should be V3 over V4 raised to K. Okay? So I can use this immediately because P sub 3, we can solve that using combined gas law or equation number 5. So this is equation number 7. Next. So the next thing that we can solve is for heat rejected. Okay? So for heat rejected, it is already given, this one. So that is negative MCV T4 minus T1. Okay? So as you can see, if we'll return to equation number 1, so let's rewrite it here in the bottom. So we have the efficiency is equal to 1 minus, that is T4 minus T1. So T4 minus T1 over T3 minus T2. So let's double check. Okay. So now we are able to solve for T3 and T2 simultaneously. Okay? So let's substitute this T3 with this T3. Okay? And T2 with T2 as well. So efficiency is equal to 1 minus T4 minus T1 over T3. We write it as T4 raised to RK raised to K minus 1 minus T2. So we've solved for T sub 2. That is T1. So that is equation number 2. T1 RK raised to K minus 1. So that is T1 RK raised to K minus 1. So as you can see here in the denominator, we have a common factor, that is RK raised to K minus 1. So we can factor that out. We will have efficiency is equal to 1 minus T4 minus T1 over, factor out RK raised to K minus 1, that is RK raised to K minus 1 quantity T4 minus T1. So as you can see, T4 minus T1 in the numerator and the denominator will cancel out, leaving us with the simplified version of your efficiency, which is 1 minus 1 over RK raised to K minus 1. So you can immediately use this one once you are given the value of your compression ratio and K. Okay, so this one is equation number 7. So for the next video, we will try to apply this one in a sample problem of Otto cycle. So I hope to see you there, and let's try to practice operations of gas cycles. Okay, so I hope you learned something, and I see you on the next video.